Welcome back to the channel. So today in this video we are going to attempt question number 1 of exercise 2.3 chapter relations and functions of class 11th CBSE mathematics. So the question is, which of the following relations are functions? Give reason. If it is a function, then determine its domain and range. Now what are functions? Let's go through the definition. A relation f from a set A to a set B is said to be a function if every element of set A has one and only one image in set B. So a function is a relation. It's a special type of relation where every element of set A has one and only one image in set B. Now to understand this, let us take an example. Take for example, we are given with a relation where x comma y such that y is equal to 2 times x and x is equal to 1, 2, 3, 4 and 5. Now let us represent this very relation in raster form. Here if we'll plug in the value of x as 1, we'll be having value of y as 2 according to this relation. Plug in the value of x as 2, we'll be having value of y as 4. If value of x is 3, value of y will be 6. If value of x is 4, value of y will be 8. And if value of x is 5, value of y will be 10. Value of x can go up to 5 as per given condition. Now the second element of each ordered pair forms the image of first element. That is 1 in this case. Similarly, 4 is the image of 2, 6 is the image of 3, 8 is the image of 4 and 10 is the image of 5. Here one can observe that every element has its unique image. So this relation is a function. Another point to be noted is that the first element is said to be pre-image of second element. So here 2, 3, 4 and 5, they are all pre-images. Now let us consider a few more examples. Suppose we are given with a relation where the elements are 1, 2, 2, 3, 5, 2 and 7, 9. Here consider this very first element and this third element. One can observe that both these elements are having same image. That is, 1 is having 2 as image and 5 is also having 2 as image. This relation will also be considered as a function. So remember that in case of a function, different elements can have same image. So this is a point we noted, that different elements can have same image. That's the reason why this relation will be considered as a function. Now let us consider another example. Let us suppose we are given with a relation having elements as. The first element is 1, 2. The second element or ordered pair is 2, 3. The third element is 1, 5. And the last element is 6, 7. Now here consider these two elements, that is the first element and third element. Here one can observe that one has 2 as image and one has 5 as image. So here same element is having different images. This relation will not be considered as a function. So this is not a function. So this is another point to be noted, that same element cannot have different images. So this is another point to be noted, that same elements cannot have different images. So these are the 2 points to be noted, that a relation will be a function even if different elements have same image. But a relation will not be a function if same element has different images. Now let us understand what real valued functions are. Real valued functions. A function which has either r, that is real numbers, or one of its subsets as its range is called a real valued function. So real valued functions are nothing but these are those functions which have either r or one of its subsets as its range. And if its domain, that means the domain of the function, is also either r or a subset of r, then it is called a real function. So if domain is also either r or a subset of r, it is called a real function. Now before attempting question number 1, let us go through some functions and their graphs. So here we are going to discuss some functions and their graphs. These functions are: number 1, identity function. Number 2, constant function. Number 3, polynomial function. Number 4, rational function. Number 5, modulus function. Number 6, signum function. And number 7, greatest integer function. So these are the types of functions which we are going to discuss and also see how their graphs work. Let's go through the first function, that is identity function. A function f from r to r is an identity function defined by y is equal to f of x is equal to x. So it's a function where input and output are always equal. Take for example, if x is 2, then f of x, which is y, it will be also 2. Similarly, if x is 1, then f of x will also be 1. If x is 0, then f of x, that is y, will also be 0. Similarly, if x is negative 1, then f of x will also be negative 1. If x is negative 2, then f of x will also be negative 2. Now let us see how graph of this function works. Here we have y is equal to x. So obviously this will be a graph passing through origin. One can observe that for value of x equal to 2, we are having value of y equal to 2 as well. Similarly, for value of x equal to negative 2, we are having value of y negative 2 as well. One can easily determine with the help of a graph whether the given relation is a function. For that very thing, we'll have to draw a vertical line and check whether this vertical line intersects at only one point with the graph. If it is intersecting at only one point with the graph, we can say that this relation will be a function. Here in our case, this vertical line is intersecting only at one point, whether it be anywhere on the graph. So obviously this graph represents a function. So this test is called vertical line test. Remember, if the graph intersects at 2 or more than 2 points, then that graph will not represent a function. Towards the second type of function. This is constant function. So a function f from R to R is a constant function where y is equal to f of x is equal to c, which is a constant. So which means whatever the input will be, the output will be a fixed value. Take for example, if value of x is 2, let us take value of y as 5, a constant in our case. If value of x is equal to 1, then value of y will again be 5. Similarly, if value of x is equal to 0, value of y will again be 5. No matter what the value of x will be having value of y as a constant. So for any value of x, y will not change. Now let us see how graph of this function works. Here we have value of y equal to 5, which is a constant value in our case. Now obviously in this case, our graph will be a line parallel to x-axis. Towards the next function, the third function, polynomial function. It's a function from R to R where y is equal to f of x is equal to a0 plus a1x plus a2x squared plus so on plus an x powered n. Here n is non-negative integer and a0, a1, a2, an, they all belong to real numbers. Take for example, we have a function from R to R defined by y is equal to f of x is equal to x square. So it's a type of a polynomial function, an example of a polynomial function. Now let us suppose if the input, if the value of x is 2, we'll be having f of x, which is x square, it will be equal to 4. Similarly, if x is equal to 1, we'll be having f of x 1. If x is equal to 0, we'll be having f of x equal to 0. If x is equal to negative 1, we'll be having f of x equal to 1. Similarly, if x is equal to negative 2, we'll be having f of x equal to 4 and so on. Let's represent this very function with the help of a graph. So here we are having y is equal to x squared. So this will be our graph. So here again, take for example, for value of x equal to 2, we are having value of y equal to 4. And for value of x equal to negative 2, we are having value of y again equal to 4. Similarly, suppose we have another polynomial function y is equal to x cubed. So here one can observe that for value of x equal to 2, value of y is 8, and for value of x equal to negative 2, value of y is negative 8. So this is another example of a polynomial function. Towards the next type of function. This is the fourth type, rational function. These are the functions of type f of x over g of x. That is, these functions have a numerator and a denominator, such that f of x and g of x are the polynomial functions of x defined in a domain. Where g of x is not equal to 0. Take for example a function from r minus 0 to r, where f of x is equal to 1 over x and x belongs to real numbers minus 0. So this is an example of a rational function. Now here, if x is equal to 2, we'll be having f of x equal to 1 over 2, and that will be equal to 0.5. Similarly, if x is equal to 1, f of x will be equal to 1. Now x cannot be equal to 0. As we know, denominator of a rational function cannot be 0. So now if x is equal to negative 1, f of x will also be negative 1. And similarly, if x is equal to negative 2, we have f of x equal to minus 0.5 and so on. We know that a Cartesian plane is divided into 4 parts called quadrants by the axes, which are x-axis and y-axis. So this is our first quadrant, this is second quadrant, this is third quadrant, and this is fourth quadrant. In first quadrant, both x and y are positive. In second quadrant, x is negative and y is positive. In third quadrant, both x and y are negative. And in fourth quadrant, x is positive and y is negative. Now from these two values, that is x is equal to 2 and x is equal to 1, we are having f of x, that is value of y, as 0.5 and 1. Here input is positive and output is positive, meaning that values of x are positive and values of y are positive as well. So the first part of this very graph will lie in first quadrant because both x and y are positive. Similarly, for x is equal to negative 1, f of x is negative 1. And for x is equal to negative 2, f of x, that is y, it is negative 0.5. Which means that if the input is negative, the output is also negative. That means both values of x and y are negative. So this very part of the graph will lie in this very quadrant of the Cartesian plane, which means that this graph will be divided into 2 parts. Now let's see how graph of this very function works. Here we are having y is equal to 1 over x. As stated earlier, this graph is divided into 2 parts, one lying in the first quadrant and the other part lying in the third quadrant. So it's a graph of this very function, that is rational function. Towards the next function, it's function fifth, modulus function. Now what is a modulus function? Here we have a function from R to R defined by f of x is equal to mod x. Here we have two conditions, that is f of x will be equal to x if x is greater than or equal to 0, and f of x will be equal to negative x if x is less than 0. Suppose if we'll plug in the value of x equal to 2, f of x will be equal to 2. As we know, f of x remains x if x is greater than 0. Similarly, if x is equal to 1, we'll be having f of x again equal to 1. And if we plug in value of x equal to 0, f of x will be 0. Same reason that if x is greater than or equal to 0, f of x remains x, meaning that its value doesn't change. Now, if we'll plug in the value of x equal to negative 1, in this case, value of f of x, that is y, will be positive 1. Because when x is less than 0, here we have plugged in the value of x as less than 0, that's minus 1. Our x will get an extra negative, which means negative number times a negative number will give us a positive number. Similarly, if we'll put the value of x as negative 2, we'll be having value of f of x as positive 2, and so on. So we'll have to remember that in modulus function, whether x is positive, negative or 0, mod of x or modulus of x or x modulus will always remain positive. Now let us see how graph of this function works. Here we are having y is equal to mod x. Here, take for example, if value of x is 4, value of y remains 4. And if value of x is negative 4, value of y again comes out to be positive 4. And for value of x is equal to 0, value of y is 0. So this is a graph of the modulus function. Moving towards next function. Number 6, signum function. A function f from R to R defined by f of x equal to 1 if x is greater than 0, 0 if x is equal to 0, and negative 1 if x is less than 0 is called a signum function. Meaning that for any value of x greater than 0, we'll be having value of y always equal to 1. For value of x equal to 0, value of y will be 0. And for any value of x less than 0, the value of y will be negative 1. For example, if x is equal to 2, f of x will be equal to 1. Similarly, if we'll put value of x as 1, f of x or value of y will again be equal to 1. As these both values are greater than 0, so our output will be equal to 1. Now, if x is equal to 0, f of x will be 0. As for input of x equal to 0, we're having value of output, that is y equal to 0. Now, if x is equal to negative 1, f of x will be negative 1. And if x is equal to negative 2, f of x will again be equal to negative 1. Here again, for value of x less than 0, the value of y will always be negative 1. And these two values, that is negative 1 and negative 2, are less than 0. And the values can go so on from both sides. Now let us see how graph of this function works. We know that for values of x greater than 0, we'll be having value of y equal to 1. So take for example, if value of x is equal to 2, we'll be having value of y equal to 1. Similarly, for value of x equal to 4, we'll be having value of y again equal to 1. Similarly, for value of x equal to 6, we'll be having value of y again equal to 1. So here in this condition, our graph will be somewhat like this. We know that for x equal to 0, y is not equal to 1. So here on y-axis, we'll be having an open interval. Now for x equal to 0, we have y equal to 0. So this will be represented by origin. Also, we know that for values of x less than 0, value of y is always negative 1. Take for example, for x equal to negative 2, y will be negative 1. For x equal to negative 4, y will be negative 1. For x equal to negative 6, y will again be negative 1. So here in this condition, our graph will be somewhat like this. Here again, on x-axis, we will be having an open interval. As for x equal to 0, y is not equal to -1. So this is how we can represent signum function with the help of a graph. Towards the last function. Number 7. Greatest integer function. So here a function f from R to R is defined by f of x is equal to x in these brackets, which is how we denote this function. Here x belongs to real numbers, which means that x assumes the value of the greatest integer less than or equal to x. Now such a function is called the greatest integer function. So from this very definition we have the greatest integer function will assume value -1 for x greater than or equal to -1 but less than 0. Similarly, this function will assume value equal to 0 for x greater than or equal to 0 but less than 1. Similarly, this function will assume value equal to 1 for x greater than or equal to 1 but less than 2. This function will assume value equal to 2 for x greater than or equal to 2 but less than 3, and so on. Suppose if we'll plug in the value of x as 2.3, the greatest integer function will give value of y equal to 2, which means that here x assumes the value of the greatest integer less than or equal to x. So here the integer nearest to 2.3 but less than 2.3 is 2. Similarly, if x is equal to 1.5, f of x, that is the greatest integer function, it will give value of y equal to 1 because the integer which is nearest to 1.5 is 1. In the same manner, for x equal to -0.7, our function, that is f of x, the greatest integer function, will provide the value of y equal to -1. Here again, the nearest integer to -0.7 is -1. In the same manner, if x is equal to -1.5, then our function, that's the greatest integer function, will give output equal to -2. Now for x equal to, suppose 3, the greatest integer in this case will be equal to 3 itself, and so on. Now let us see how this function can be represented with the help of a graph. For values of x greater than or equal to 2, we'll be having value of y as 1. For values of x greater than or equal to 2 but less than 3, we'll be having value of y as 2. Similarly, for values of x greater than or equal to 3 but less than 4, we'll be having value of y as 3. Similarly, for values of x greater than or equal to -1 but less than 0, y will be -1. For values of x greater than or equal to -2 but less than 1, y will be -2. And for values of x greater than or equal to 3 but less than -2, y will be -3. This graph looks somewhat like steps of a staircase. The reason why this function is also known as the step function or the floor function. Now let us move back towards our question. The question was, which of the following relations or functions give reasons if it is a function, determine its domain and range. We already know what a function is. So in case of a function, we have a relation where every element of set A has one and only one image in set B. Here we have part first. The given relation is with elements 2, 1, 5, 1, 8, 1, 11, 1, 14 comma 1 and 17 comma 1. We already know that different elements can have same image, and here we don't find any element having two or more different images. So this relation is a function. Now we have also been asked to find the domain and range in case the given relation is a function. So since this very first part it is a function, here domain of the function will be. We know what domain is. It is a set of all the first elements of ordered pairs. So here the first element of each ordered pair is 2, 5, 8, 11, 14 and 17. So this set will be having these elements. That is 2, 5, 8, 11, 14 and 17. And range. We know what range is. It is a set of all the second elements of ordered pairs. So here our range will be having elements as. So here our range will be having only one element, that is 1. Since repetition is not allowed while writing a set in roster form, so range here in this case will be a set containing only one element, that is 1. Towards part number 2nd, here we have a relation with elements as 2, 1, 4, 2, 6, 3, 8, 4, 10, 5, 12, 6 and 14, 7. Here one can observe that the first element of each ordered pair is having a distinct image. So this relation is a function. Here 2 has image 1, 4 has image 2, 6 has image 3, 8 has image 4, 10 has image 5, 12 has image 6 and 14 has image 7. So this relation, it is a function. Now what is domain of this function? So it's the set of all the first elements of ordered pairs. Here this set contains elements as 2, 4, 6, 8, 10, 12 and 14. So these are the elements of this very set. That is 2, 4, 6, 8, 10, 12 and 14. And what will be range of this function? Here again is the set of all the second elements of ordered pairs. So this set will be having elements as 1, 2, 3, 4, 5, 6 and 7. So the elements of range are 1, 2, 3, 4, 5, 6 and 7. Now in part number 3rd, we are given with a relation having elements as 1, 3, 1, 5 and 2, 5. Here we observe that in first ordered pair, 1 has image as 3 and in second ordered pair, 1 has image as 5, which is not possible as we know same element cannot have different images. So this relation is not a function. It is not a function. Hope this makes sense. Do subscribe to the channel for more such content and thanks for watching.